All right, in 6.2, we are going to kind of open up our tools a little bit more, maybe do some more advanced tools in our set so that when we go forward to 6.3 and we actually start looking at our whole goal for this chapter, which is what do I do if there's not a solution to the system of equations? How can I approximate a solution to this system of equations, or how close can I get? Today, we're going to keep looking at orthogonality, and we're going to, I'm going to kind of speed through the first couple pages, or well, at least the first page, because this is kind of just a new definition to where I want to get to something, the most important part of this lesson, which is how do I rewrite a vector in terms of two different components which are important, because that's going to end up being the big tool that we use later. So first definition, an orthogonal set, okay, if the vectors in the set, when dotted with each other and not with itself, they all equal 0. So that's a whole bunch of different permutations of that, different combinations, but a good way to test it would be just dot, especially for small sets, dot each vector with the other vectors in the set and assure that they become 0 at the end. If that's true for all the vectors, it's an orthogonal set. Notice that it's not that it has to be dotted with itself, just dotted with a different vector in the set, make sure that equals 0. They are all orthogonal to each other. Another great result of this is that this is going to be another example of a basis. And we'll talk about that in a little bit later. But again, another example down here at the bottom is this vector set, an orthogonal set. No, even though when I dot v1 and v2 I get 0, v1 and v3 I get 0, when I dot v2 and v3, I'm getting something that is non-zero, therefore it ruins it for everybody. The set is not orthogonal. Okay, theorem at the bottom. So suppose we have a set, u1 through up, okay, and it's an orthogonal set of non-zero vectors. Okay, well, that makes sense because it's, okay, good question. Can the zero vector be a part of an orthogonal set? I would say yes, because any vector dotted with a zero vector is still 0. So it doesn't necessarily, an orthogonal set could have a 0 vector in it. But if we have an orthogonal set of non-zero vectors in Rn, then 1, it's linearly independent. Okay, we knew that it couldn't be linearly independent if the 0 vector is in there, because the 0 vector makes sets, the 0 vector itself is linearly dependent, but is also a basis, and this is where I want you to be careful. It's a basis for the subspace spanned by S, not necessarily a basis for Rn. This is a great true-false question. Okay, it's not necessarily a basis for Rn because I did not tell you whether or not the number of vectors in the set was equal to the n dimensions that we're looking for. So I know that it's linearly independent, but all I know is that it spans. This is a basis for the set spanned by S. I would have to have more information to know if that set spanned all of Rn. So an orthogonal basis for a subspace of Rn, okay, it's just a basis. It's also an orthogonal set. Okay, I'm sure you can think of one. That would be something that we've already talked about. You could double check it. The easiest one would be like the standard basis in R3. That's definitely an orthogonal basis. Again, a reminder from previous chapters, chapter 4, we can have many different bases. This is one that just has an additional condition, and that additional condition is that all of the vectors in the basis are orthogonal. Okay, all right, so a little proof that we want to do though, okay, regarding kind of the same thing. So let's say I have a set of vectors, and you know that it is an orthogonal basis for a subspace W. Y is in that subspace, okay? So Y is in W. We want to find constants, okay? So we're just looking for the constants so that Y is a linear combination of the basis vectors, so that Y is in the span. Now, so we're looking for just kind of a specific, we're looking for a general formula. Notice we didn't include any numbers in this example, so we're not going to get a very specific answer, but we can get a very general answer in which later examples we could plug information into. So I've given you a hint here. begin with dotting y with one of the vectors in the basis. So if I dot y with u, and let's just say the first one, I can describe this as, thinking back to 6.1, the constant c1, u1, plus c2, u2, all the way up to cp, up. This is a description of y, because y is a member of w. And if y is a member of the subspace, that means it can be described as a linear combination of the basis vectors. Okay, so this is y, but then we dotted it with u1. So this is where we added in kind of a larger combination of dot product vectors in the last lesson, 6.1. You could pause here and look back if you need to. But if I apply that here, that means that I can kind of distribute and reassociate at the same time. So C1, U1 dotted with U1, plus C2, U2 dotted with U1, so on, plus so on and so forth, until CP, UP dotted with U1. Now, the most important thing is, this is an orthogonal basis. So any vector that's in the basis dotted with another vector in the basis, like here and here, should equal 0. So all we're left with is C1, U1 dotted with U1. Now, remember, we don't know what that is. We're not sure if it's 0. It's probably non-zero, but that's kind of our answer here. We've got y dotted with U1 equals C1 times U1 dotted with U1. And we were looking for a description of the constants, so if I solve for C1, I am getting that y dotted with U1 divided by U1 dotted with U1 is equal to C1. And if we continue doing this, we could do this over and over and over again. We could be lazy and say etc. or C2 through CP. Okay, all of them will have kind of the same formula. And that's what Theorem 5, all the constants, will have all the same formula. And that's kind of what Theorem 5 is getting at. And this kind of looks like, if you think way back to multivariable calculus, this kind of looks like the component. It's very close. The only difference is a little bit about the denominator. So what Theorem 5 is saying is, again, if I have an orthogonal basis for a subspace, then each y has a unique representation as a linear combination of u1 through up. That makes sense because every vector in the subspace should be able to be described by the basis vectors. That's the whole point of a basis. But what we're advanced in saying now is, because it's an orthogonal basis, we have a very specific formula for figuring out each of those constants, which is actually what we're looking for when we are solving an equation. So in example 4, okay, when I ask you to express y as a linear combination of this orthogonal basis, what we're asking is, what would the constants be for each vector? Or, alternatively, another way to say that, what would I need to multiply the matrix A by, there we go, so that I get 3, 7, 4. That's solving AX equals 0, which we've been doing by row reducing. But if we use Theorem 5, we have a little short, a shortcut, now I get it, this is way easier than row reducing by hand, but maybe not way easier than just row reducing in your calculator. But our idea is that C1, which will be the first entry of X, should be equal to y dotted with U1 over U1 dotted with U1. Which in this case, we'll call this one U1, U2, and U3, because that's the order I put them in. If I dot y with U1 for the numerator, I'm getting 3 minus 7 plus 0. If I dot U1 with itself, I am getting 1 plus 1 plus 0. So here I'm getting negative 4, writing is bad, over 2, so negative 2. So the first entry of my solution is negative 2. And we'll keep going. Y dotted with U2 over U2 dotted with U2 is going to be 3 plus 7 plus 0 over 1 plus 1. So this will be 5. And last but not least, C3 will be y dotted with u3 divided by u3 dotted with u3. So that gives me 0 plus 4 divided by 0 plus 0, 0 plus 1. So the final answer is 4. So we have found the solution using just the dot product. To express y as a linear combination of the orthogonal basis, y will be equal to negative 2u1 plus 5u2 plus 4u3. Or alternatively, the x vector that is a solution to this matrix equation will be negative 2, 5, 4. Okay, there you go. Just some easy math if we're not using our calculator. Now, on to the big tool for today, orthogonal projections. And yes, this is going to end up being a little bit like multi. So our goal here, and it'll be important to draw this diagram with me. Our goal here is going to be to describe this vector y as two different pieces. We want y, we'll put some dotted lines. We want y to be described as a component parallel to u, or a multiple of u. And let me highlight u for you. U is not necessarily that vector there. It's this whole vector here. That is where u is. Okay, u is kind of this whole thing. You can also think about u being one representative for a whole plane. Okay. We also, the other component, we want to describe it as a component in one direction and a component perpendicular to that direction of u. So this formula over here on the left says we want to describe y as two components, a multiple of u, which we will call y hat, and a multiple of a vector perpendicular to u, which we will call z. Okay, and this is kind of why last time we wanted to talk about, one, we wanted to review the dot product as a way to prove that two things are orthogonal, but two, we wanted to talk about vectors that are all the vectors that are perpendicular to a certain plane, aka the orthogonal complement. So if I do a little math off to the side, don't forget, you can solve for that orthogonal piece by, if you know y, and you can find the projection of y onto u. Okay, so another way to describe this is here, y equals some scalar times u plus z, that perpendicular vector. And again, z will be equal to y minus that scalar times u, or y hat, whatever you want to call it. Maybe I'll highlight this part in green instead so we keep our colors consistent. Okay, and okay, yes. Now remember, y hat, I realize I'm looking at my color choices here. Y hat is, while it is parallel or in the same direction as u, y hat is this portion. It is the projection of y onto u. Okay, so there are a lot of different formulas here, but if you are, and we'll walk through that in a second, I want to get to the main ones that you will need. Okay, because we've kind of, if you think about what we learned in multi, you already know what we're looking for here, how to write y. Because I've said it several times. Oh, dang it, let me keep my colors. Y hat is the orthogonal projection of y onto u. Okay, but that, if you remember from multi, was y, what I was trying to project, dotted with u, what I want to project it on, divided by u dotted with u, times, because it has to be a vector, the actual vector u. The first part was a scalar. It was the alpha that is scaling u, and u was the vector we were trying to project onto. So this is the projection of y onto u. Okay, not different from multi. The difference is I need z to also be a vector. So z is not actually related to this component formula. Okay, these are going to be different. Z is the other portion of y, the vector we are trying to describe differently, minus the part in the direction of u. Okay. Okay. You can also describe this. I feel like this is the simplest, this is the way you're going to want to remember it, but you could also plug the formula for y hat in there. Times u. Just remember that z is a vector. It's not a scalar. So it needs to have components. It can't just be a dot product. It actually has to be multiplied by a vector. Okay. So there are a couple of things. One to point out before we keep moving on. And one, this is the same formula here because remember that the magnitude of a vector is really the square root of it dotted with itself. So if I square that side, I just get u dotted with u. So magnitude squared is the same as u dotted with u. Okay, we got rid of the square root part. I think, for the sake of time, I'm actually not going to walk through kind of this progress. I think it makes sense if we just look at it kind of theoretically from the multi-way. But if you need to walk through these formulas here that we've talked about, take a look at the fill notes. A lot of this has to do with the fact that z and u should be orthogonal, making some substitutions from the formula we defined here, and then developing a formula for the constant by which I'm going to scale the vector u. But if we're coming from the multi-direction, I think it makes sense more to think of y hat as the projection of y onto u. Okay, so how do we use this in practice? Why is this useful? So we've got two vectors, y equals -8, 4, and u equals 3, 1. Okay, so here's u. Let's give it a nice color. Let's try that again. Okay, and if that's not big enough, there it is, 3, 1. And I'm going to actually draw a y as well. We'll draw it in red. So -8, 4 means moving to the left. Okay, this will be y. Okay, and I want to know the distance from y to the line through 0 and u. Okay, all right, so let's draw that line out a little bit. Okay, all right, and then I want to measure, okay, so this is u, and I assume that this was the origin. Let me label it. Okay, all right, so I want to measure the distance between y, the end of that vector, and this line. And we talked about measuring distance before, but just in case, really, we want to measure this distance here, making an orthogonal, kind of a right angle with that line. Okay, we're going to call this z. All right, so we want to find the magnitude of z. And this is where what we just did is super helpful. So how can we find what z is? Knowing along this line is not necessarily an axis that we're used to. So to find z, we're going to find magnitude of z. Okay, so first thing we're going to do is we're going to find y hat. We're going to project the vector y down onto the line. Okay, and then we are going to do y minus y hat to find z. Okay, so first I need to do is find y hat. Okay, all right, so that means I will find the projection, sorry friends, lose my brain here at the end of the day, of y onto u. Okay, so I'm dotting vectors together, so in the numerator, I will get y dotted with u. Again, here's our formula, u dotted with u times u. Okay, so I'm getting negative 24 plus 4 divided by 9 plus 1. All of this is being multiplied by the vector 3, 1, which I'm still going to write the linear algebra way, just for funsies, because this is linear algebra. Okay, so I'm getting 20, 10, negative 2 times 3, 1. So the y hat is the vector negative 6, negative 2. Okay, all right, we're almost there. Z will then be y minus y hat, because they are z and y hat are going to be orthogonal to each other. I know that they're orthogonal because y hat is parallel to u and z is perpendicular to u. Okay, so y is negative 8. 4, wow, I don't know why I tried to write that as negative, minus negative 6, negative 2, giving me negative 8 plus 6, which is negative 2, and 4 plus 2, which is 6. So that's z. But I want to find distance, so I'm finding magnitude of z, which would be the square root of z dotted with itself. I'm writing it backwards, 36 plus 4, square root of 40, a little simplifying, 2 square root of 10. Distance is 2 square root of 10. Okay, so that was a useful tool. We are definitely going to use this tool, though, to kind of this measuring of distance by using these orthogonal projections more when we're trying to find the solution that is closest to the solution we're looking for. Okay, how close can we get to actually solving a system of equations that has no solution? So another tool we're going to use real quick is an orthonormal set. And the only difference between this and an orthogonal set is right here. A set of vectors here is an orthonormal set if it's an orthogonal set of unit vectors. Okay? Remember, we used the phrase normalize a vector to indicate that we had shortened its length to be 1. Okay, and if W, a subspace, is the span of that orthonormal set, then this is you could make an orthonormal basis. Again, still a basis, just more restrictions now. So how do I know which sets are orthonormal? Well, first test if it's orthogonal, and then afterwards see if they are unit vectors. Okay, does their length equal 1? Okay, so we'll do one of these, and then you can look at the field notes for the second one. So let's do B. Yeah. Are they orthogonal? So is this an orthogonal set? So if I'll call this U and V again. So if I dot U and V, do I get 0? Well, I get negative 2/9 plus 2/9 plus 0. So yes, this is an orthogonal set. Are they orthonormal, though? Are their lengths 1? So if I find the length of U, keep my vector notation going up here, I'm getting the square root of 4/9 plus 1/9 plus 4/9. So this one is good to go. Okay, what about V? I'm getting 1/9 plus 4/9 plus 0. So this is going to be the square root of 5/3 is the length. And that is not a normal vector. So I need to normalize V. Which means I would divide by that length. So my new orthonormal set would be the first vector left alone, negative 2/3, 1/3, 2/3. And the second vector scaled, so that has a length of 1. So dividing by square root of 5/3 means multiplying by 3 over square root of 5. I am not going to normalize I'm not going to rationalize because, wow, I don't like rationalizing. I honestly don't sometimes know why we do it, other than for the unit circle. But there it is, our orthonormal set. Now, is multiplying by a scalar going to change the fact that they are going to be orthogonal? No. I am scaling the whole vector, therefore my calculation up here would be just multiplied by another, each term would be multiplied by that scalar. The result should still be 0. So multiplying by the scalar does not change how orthogonal they are. Okay, couple last things here, and I put them in the field notes, but I wanted to talk through them a little bit, just so we didn't have to write out all these little U1 transpose. So let's say we have a matrix made up of 3 columns, U1, U2, U3, but those 3 columns are an orthonormal set. Okay, so 1, those 3 vectors are orthogonal to each other, and 2, their lengths are 1. Okay, then we want to find out what happens if I multiply U transpose with itself. Okay, so since I did U transpose, that means I would have to transpose each column, okay, to be in a row. So that means that they kind of go across now. And I multiply them by these 3 columns. So the result will be 3 by 3. Now I don't 3 by 3 in notation. This is kind of where our partitioned matrices are coming in. Each of these is kind of partitioned into a vector itself, okay, which is another word for matrix. So when I multiply them together using normal matrix operations, this is what I get. Okay, U1 make sure the order is the same. U1 transpose times U1, U1 transpose times U2, going down, all the way down. Okay, good. Now, the fact that this is an orthonormal set, though, means that some of this will go away. When okay, and remember, the dot product U1 dotted with U2, in our definition from last class, 6.1, is really, this is U1 transpose times U2. Okay, that's what the dot product is equal to in linear algebra, because we cannot actually multiply 2 vectors together. That doesn't fit our matrix multiplication, because I would be multiplying something that was 3 by 1 by something that was 3 by 1, and those columns and rows in the middle don't match. So the dot product is defined by U1 dotted with U2 is equal to U1 transpose times U2, therefore the columns in the middle match. The columns and rows in the middle match. So that means if this is orthonormal, all of these are actually dot products of vectors. And if this is an orthonormal set, everything that is not a vector dotted with itself goes away, which means we get this matrix here. Okay? But a vector dotted with itself is the magnitude of that vector squared. And since this is an orthonormal set, all of the magnitudes are 1. So this means I get the identity matrix. And you can see where we're kind of going with this is I multiplied 2 matrices together and I got the identity matrix. U transpose times U equals I. So U transpose is actually U inverse, which is super cool. Okay? And that matrix is called an orthogonal matrix. Remember that the columns of U had to make an orthonormal set, though, in order for this to work. That's how it all fell together. So if we have an orthogonal matrix, we have 2 things. Okay? 1, you can conclude from this. U transpose is the inverse of U. 2, in an orthogonal matrix, the columns have to be orthonormal. Okay? All right, so last couple things we'll do here, and then we'll be done. Okay? If we have such a thing, where U is an m by n matrix with orthonormal columns, okay, then x and y are vectors, not scalars. Then the magnitude of U multiplied by x will be the same as the magnitude of just x by itself. Kind of like an identity almost. Interesting. Okay, and also U dotted with x, U times x dotted with U times y will be x dotted with y. Little proof. Okay, start from the beginning. U times x times dotted with U times y. By definition of dot product, this is the same as ux transpose times uy. Okay, and by definition of transpose, who remembers? Hopefully everybody. This will be x transpose times u transpose times u times y. But since this is orthonormal columns, we prove that the middle is the identity. This is x transpose times the identity times y. So this will really be x transpose times y, which again, wrapping back around, is the definition of the dot product in linear algebra. Ta-da! Okay, and as a result, this is connected. Because this b is true, then if I dot those two things together and I get 0, that will only happen if the dot product of x and y is 0. And that's it for today. So today, summarize, we expanded our tools a little bit. We talked about creating an orthogonal set, okay, and how that is just, we can use that as another basis. We use that to be able to solve a system of equations. And if I have an orthogonal basis, I have specific formulas for the constants that will kind of solve the vector, that will be the elements of the vector x solving this system of equations here. We talked about using an orthogonal projection to split up a vector into two different components, one parallel or in a plane that we are looking at, and one as a part of the orthogonal complement to that plane or vector. We also use that to measure distance in between two vectors, or in between a vector and a line. We also then talked about orthonormal sets. Building from orthogonal bases and orthogonal sets, we said, what if we have orthogonal vectors and their length are 1? How is that helpful? And we looked at how that gives us a new type of matrix, where the columns of that matrix are an orthonormal set. Then we have that matrix, a matrix with columns that are an orthonormal set. The transpose of that matrix will be its own inverse, and that led us to some cool properties. Okay, in 6.3, we will do more with orthogonal projections, and we'll expand into trying to find solutions or close enough solutions to systems that are inconsistent.